Here are some quick notes on virial equilibrium to accompany Chapter 2 of To Build a Star. So the virial theorem, this describes basically the energy balance for a stable bound system of some number of particles. So we're talking about something like a star that's not rapidly contracting or expanding, and we'll cover what rapid means in a little bit, or in next lecture really, and it's also kind of covered in the dynamical time, quick notes. And bound just means, it's not exploding, right? Things aren't escaping. So we can describe this energy balance with the virial theorem. This comes from Rudolf Clausius, which normally I don't point out who came up with what theorem, but this picture in Wikipedia made me laugh. So he's the guy that came up with this originally. So what we do is let's consider the total kinetic energy of our star. So we're just going to sum the kinetic energy of individual particles. Let's just use the non-relativistic form. You can do this for relativistic as well. So kinetic energy of an individual particle is going to be 1/2 mv squared. We can turn this into momentum times the velocity, right? Because mv is momentum. So mv squared becomes momentum times velocity. And the velocity is nothing other than the change in position with respect to time. So how do we deal with this change, this dot product here, the momentum dotted with change in position with respect to time? I'm going to take a detour quickly. So the time derivative of the dot product of momentum with position, this is equal to the dot product of position times change in momentum with time, plus the dot product of momentum times change in position with time. You recognize this second term is the same thing that's up here, and so we can substitute in, and you'll see why we do this in a moment. Instead of having this particular dot product, we instead will have the time derivative of the dot product of momentum with position minus the dot product of position with change in momentum with time. We're going to substitute that difference in, instead of having this thing up here. So when we do that substitution, our kinetic energy is 1/2 times the time derivative of this dot product of momentum with position minus the position dotted with the change in momentum with time. Now this momentum dotted with position, that's just a dot product, and so the result is a scalar, and we're just going to call that g. Okay, so that's defined as g. Second term is unchanged. But what we can realize is that in the second term we have change in momentum with time. That is nothing other than the force. So we have the dot product of position and force becomes our second term. That is equal to the kinetic energy. So what do we do with force? Well, okay, recall that from your intro physics, work is a force times the distance. And so that means that work is equal to minus the change in potential energy, right? That's also, or sorry, that's not what that means. That's also just true. Work is defined as minus the change in potential energy. And so given that, that means that our force is equal to the derivative of the potential. Okay, so right, because if we divide distance over here, so if we do work divided by distance, work is change in potential energy. So then change in potential energy divided by distance is work divided by distance, which is a force. Or maybe you just remember this from intro physics as well. So in any case, it's true. And therefore, when we substitute that in, 2 times our kinetic energy is equal to the time derivative of this scalar plus the dot product of the position with the change in the potential energy, which we're using omega here, because that's what's used in the textbook. Okay, so that's really just been algebra for the kinetic energy so far. So now what we're going to do is we're going to consider the average properties over time. So we're taking the time average of the kinetic energy here. The 2 can pop out, of course, but I have it inside there. The time average of kinetic energy is the time average of this quantity that we showed is equal to 2 times the kinetic energy. And as you probably know, or you can convince yourself, the average of a sum is equal to the sum of the averages. This is less clear with the time average, but with an ensemble average, so averaging over many stars, for instance, it's pretty clear that this is true, that you can go from this average to the second one here, where you have the sum of averages. So we have our time average now. And recall how you take a time average, right? So the average of some function over time, what you could do is you could evaluate that function at a given time multiplied by a little time slice and divide by the sum of time slices, right? That's what a time average is. The sum of these little time slices, that is the time tau, the interval that we're integrating over. And instead of doing a discrete sum here, we're going to take an integral, okay, because we're going to do this as continuous space, a continuous function. If we want to do this literally over all time, then our time tau goes to infinity, so we're taking that limit of tau goes to infinity, and we're integrating from 0 to tau. Okay, that's how you would do a time average. So now let's go back to our virial above. So 2 times the kinetic energy, then we have this limit as time goes to infinity of 1 over our time interval. Integrate from 0 to the time interval for this first thing. So that is a quantity related to time, so we'll take the time average there. This second one is still just our regular average in brackets. Okay. Now it turns out this first quantity is going to go to 0. Why? That's because g is just a scalar, right? It's the dot product of the momentum and the position. Those are not going to go to infinity, surely. They're finite quantities. So this is going to be finite. But tau is going to infinity. So the integral is going to be finite, and a finite quantity divided by infinity is 0. So that cancels. So then 2 times our kinetic energy is just the dot product of the position and the gradient of the potential. Okay. So to this point, up to there, this is totally general relationship. For any system where you're taking this time average, 2 times the average of 2 times the kinetic energy is equal to the average of the position dotted with the gradient of the potential. Now we're going to go to a more specific case. Let's look at potentials where the potential goes as the radius to some power. Okay. So then our position dotted with the gradient, that is just going to be, because this is only a radial potential, the gradient just becomes a derivative with respect to radius. So position dotted with the gradient is just radius times the partial derivative of the potential with respect to position. We can go ahead and plug in the functional form of our potential, as we do here, and take the derivative, and then you'll see that the r out front kind of restores the power that was reduced from the derivative. And so what you're left with is that the position dotted with the gradient of the potential is just equal to the potential times the initial power that it was raised to. Okay, so we're slightly less general now. We're assuming a radial potential. Let's get even less general. Let's go to the case of gravity. For gravity, it's a 1 over r potential. So J in the equation above is equal to -1. And so that means that this position dotted with the gradient of the potential is just equal to minus the average potential. So then finally, 2 times our average kinetic energy is equal to minus the average potential energy. Okay. And so then the total energy of our star is going to be the sum of the kinetic energy and the potential energy, but the kinetic is just minus 1/2 the potential. And so then finally the total energy of the star is 1/2 times this average potential energy, and that is going to be less than 0 because this is a bound system. Okay, so cool. So what are the consequences of this? Well, let's just consider a contracting star or some contracting cloud of gas. So our potential goes as -1 over r. You know, for gravity, it's minus g/mm over r. And then if we're going to decrease the radius, right, we're going to contract. That means that the denominator is going to get smaller, and therefore this quantity, 1 over that radius, is going to get larger. And so then the potential is going to become more negative. All right. Total energy is going to be conserved if the object contracts. So that the average energy here, or really the average is equal to the total because it never changes. The total energy is going to be equal to the average kinetic energy plus the average potential energy, and that's constant. So if our radius decreases, the potential becomes more negative. But if the potential energy becomes more negative, then the kinetic energy has to increase to compensate for that in order to maintain the same total energy because it's conserved. Now keep in mind that for a monatomic ideal gas, the kinetic energy is 3/2 nkt, right? And so then, therefore, keeping in mind that the number of particles in our star or in our cloud of gas is fixed, then if your kinetic energy is going to increase, the only way to do that is if the temperature increases. Okay, so that means, therefore, when you contract, when your star contracts or your cloud of gas contracts, your radius is smaller, potential energy has to get more negative, therefore the kinetic energy has to increase, therefore that means the temperature is increasing, and so a contracting cloud of gas increases its temperature. So then some consequences or practical examples. If I have some cloud of gas that isn't yet a star, as it contracts, what's going to happen is the temperature is going to increase, and eventually the temperature in the center of the cloud of gas is going to become hot enough to ignite hydrogen, and that is then what is called a star. In your star's lifetime, it's going to run through different fuels in the cores we'll talk about much later in the semester. So for instance, when it runs through some core fuel like hydrogen that it's burning on the main sequence, what's going to happen is it's going to run through this fuel, and there's going to be less and less radiation pressure. So it's going to contract because there's less radiation pressure pushing the star outwards. Your newly contracted core, because of the arguments above, is going to have a higher temperature, and ultimately that is going to enable fusion of some fuel that's harder to fuse, for instance, helium. And so then you're going to move from hydrogen helium to core helium burning, for instance, ultimately. And that is it for these quick notes on virial equilibrium.